In this last unit of the semester, we will be working with similarity. And similarity, remember, means that we're not working with congruent shapes. We're working with shapes that are dilations of one another. So it might be the same shape, but a different size. So with that, we need to review ratios and proportions and things like that. So in this video, I'm going to have some new vocabulary that I need you to know. A lot of this will probably look review. So I get that if you've seen this before, but I really want you to pay attention to some of the vocabulary that you probably have not seen, and then some properties. So for example, we know that a ratio just means we write it as a fraction, but here's what I want you to pay attention to. If A and B are two quantities that are measured in the same units, so if we're doing inches, so both values have to be in inches. I can't have one in inches and one in feet. You would have to convert to the same unit in order to have a true ratio. Okay, and then we can write the ratio, like I said, as a fraction, or we can write it in words like this, A to B. This is another way a fraction can be written, and then we can also use the colon. All right, so that's what a ratio is, and then reminder, a proportion is an equation that equates the two ratios. So if I have A divided by B, that would be equal to some other ratio, C divided by D. Or for example, in Algebra 1, you probably did things like x over 2 equals 3 over 5, and you had to solve for x. So reminder of some properties of proportions. We have the cross product property. That's what you use to solve things like x over 2 equals 3/5. You would multiply on the diagonals. Okay, so that's what we mean by the product. So you would have 5x equals 6, and then you would solve this by dividing by 5, right? That looks familiar, hopefully. What they mean by extremes and means. So this is some vocabulary you may not be familiar with. Means are just the diagonal going this way, and the extremes are the diagonal going this way. That's all. And so it just allows us to talk about, oh yeah, that diagonal versus that diagonal. Okay. So the reciprocal property, if two ratios are equal, then the reciprocals are also equal. Remember, reciprocals mean I'm just going to flip that fraction around, so my denominator becomes my numerator and vice versa. So that's what that looks like flipped. So when I flip that around, I get this proportion, and that is still going to be true. Notice that these are working with proportions, so these are equations that are true. All right, so talking about the extremes and the means. So then I want to talk about some more properties. The reciprocal property we just discussed, so I'm not going to discuss that again. But let's look at number 3. If you interchange the means of the proportion, then you form another true proportion. So remember, the means were this diagonal. So if I change those so that they're switched, this is another proportion. Another way of looking at that, you might think of it as, instead of writing the proportion this way, where you have A over this and C over this working vertically, this is working horizontally. So if I go horizontally, A is on top with the C, so now I change that to be vertical, and B is horizontal with D, so I made that into the vertical component. A lot of people like to think of it that way as well. Either way, I need you to know that those are the same proportion. And that's why it really doesn't matter when we write a proportion which one you start with. You just got to match up your second ratio with the one you originally put. Okay. Also, here's another one you probably haven't used yet. In a proportion, if you add the value of the ratio, each ratio's denominator, so these are the denominators, to its numerator, then you form another true proportion. So look at what we did here. So we added that to that numerator. So I have A plus B over B and C plus D over D. That is going to be true as well. And here's why. If we think about this algebraically, remember, if I have two things added over a single denominator, I could split that up into two separate fractions. typically we don't work backwards this way. Typically when we see two separate fractions, we combine them, we get a common denominator and combine those numerators. But if they're already combined and I split them up, look at what I have. I have a over b plus b over b. What is b over b equal to? That's just like 1, right? So then over here, if I have c over d plus d over d, again, d over d, that's just another way of saying plus 1. So all we've done when we did this property is we just added 1 to both sides, and we already know that we can do that. That's the addition property. All right, so just to get some practice. So how do we use this? So how can we rewrite these proportions? So I have a over x equals b over 5. So look at what they did here. Now they're writing it a over b. So they were going horizontally. So then I should be doing that as well. Or you can think of it as they switch the means. So b is over here, so x should be over here. And then 5 should stay exactly where it is. Next one, number 2. I originally have z over x equals y over c. So what happened over here? I have c over y. So what they did is they flipped those fractions around. They did the reciprocal. So the reciprocal of c over y should be the reciprocal of that x and z. So I should put x on top as well and z on the bottom. Okay, so that's the reciprocal property. In this next one, number 3, I have 7 over 12 equals 31 over y. And now I have 19 over 12. So I have a completely different number. This is that last one we were just talking about. So if I add this denominator up here, that's actually going to give me 19, right? So that's what they did. So then that means I needed to take this denominator and add it up here. And that's how I know what my new fraction will be. So that'll be 31 plus y. And I just have to keep it like that because obviously those are not like terms. And then number 4, we originally have 3 over 4 equals 5 over x plus 2. And now we have another completely different number. So when you see that new number, check to see if what they did was add the denominator to the numerator. So did they add that? 3 plus 4 equals 7? Yeah. So that's where they're getting that 7. So then that means we have to take this denominator and add it up here. So I have to do 5 plus x plus 2. So if I combine those like terms, that'll be x plus 7 over x plus 2. And that would be that equivalent proportion. So those are using those properties we just discussed. Let's use them now to help us solve some geometry problems. So we have the area of an isosceles triangle is 36 square inches. Okay, so let's first, anytime you have a word problem without a diagram, draw a diagram. So I'm going to draw an isosceles triangle. And we know that the area of this is 36 square inches. So I'm going to make that isosceles by doing that. Okay, the ratio of the length of the triangle's base to the height. Okay, so we got to know where's the base of the triangle and where's the height. So here's the base. Remember, the height goes perpendicular through that vertex. Perpendicular to the base through the vertex, so that's our height. And we don't know what those are, right? But I do know that whatever the base is, it's going to be twice as big as the height because the ratio of the base to the height, so b over h, is equivalent to this ratio they gave me, 2 to 1, 2 over 1. Okay, so if I reduce my base over height, it's always going to reduce to be 2 over 1. Okay, so the base is always going to be twice as big as whatever the height is. Okay, so what we can do is instead of writing this as h and b, I can write it with just one single variable. I can say instead of doing b is going to be twice as big as the height. Okay, so instead of b, I'm using 2h. Now, why would I want to do that? Well, they gave me the area, and I know that the area formula is 1/2 base times height. So I'm trying to figure out, okay, what is the actual height? Because they're wanting me to find the perimeter. So I have to find something. So we're going to have to do some work to figure out one of these variables. So all I did was use that ratio to rewrite my variables. Okay, so instead of b and h, I'm going to write 1/2. Instead of b, I'm writing 2h, and h is just going to stay h. Okay, so pause that, make sure you understand where I'm getting 2h and h. All right, and if you still have questions after the video, then ask me in class. And remember, we said that this area is 36 square inches. So we're going to solve this. So I have 36. If I do 1/2 times the 2, that's just going to be 1. So I'm going to have h times h, 1h times h. So this is going to be 36 is equal to h squared. If I square root both sides, I'm going to get h equals 6. And I'm going to ignore the negative 6, right, because I can't have a negative height. So this means that my height is 6 inches. Okay, so I'm going to redraw this triangle just so I can label it with the numbers that we know. So that's 6 inches. That means that this base has to be 12 inches, right? It has to be twice as big. All right, so how are we going to find the perimeter? We have to find those hypotenuse, right? So let's think about, if those are the hypotenuse, what is each of these lengths? So that base has to be cut in half equally, and remember we did isosceles triangles and why these would be congruent triangles and these would be the same. So these are both the same. So if they're the same and they add up to be 12, each of these would also be 6 inches long. So how are we going to find the hypotenuse? Well, what kinds of triangles are these? This is a right triangle, so that means we can do the Pythagorean theorem. Look at all of this geometry that we're using in one single problem. I know you guys are probably groaning by now. So we have that. And we take the square root. So we're going to get the square root of 72. And then if we simplify that a little bit, that's going to be, this breaks down into the square root of 36 times the square root of 2. So this is going to be 6 root 2. Okay, so all these 6's everywhere. So I got 6 root 2 for this hypotenuse, and I would get the same thing over here, right? So we're almost there. We can finally do the perimeter. Perimeter means I got to add up all of the sides. So I've got my 6 root 2, my 6 root 2 over here, and we said the base was 12. So if I add up all of those, remember, which ones can we add together and which ones can we not add together? I can combine these together, but not the 12. So if I combine those, that'll give me 12 root 2. So this would be my perimeter. All right, let's do another one. More geometry. Points X and Y lie on WZ. They didn't give me a diagram, so I'm going to draw it. So I'm going to draw a segment WZ. And they said X and Y lie on it somewhere, so I don't know what order they lie on. I don't know if they're in the middle or anything like that. I'm not even going to put it there. I'm going to put it somewhere random so I don't try to assume anything. Okay, so what it says is WX, so the ratio of this line to XZ is 2 to 5. And then the ratio, so this is 2 to 5. And I don't want to write 2 and 5 because that's assuming that if those can never be reduced, they're already reduced. So I really want to write, like, I don't want to use X, but this is 2 times some number, and that's 5 times some number. So if I reduce that, the A part goes away, but I want to allow for that to be different multiples of 2 and 5. And then here they say WY, and then ratio to YZ is 7 to 8. Okay, so again, I'm going to write a variable. I'm not going to write A because it might be a different multiple than the other one, so let's do like B. So this would be 7B compared to 8B. All right, so again, those variables are just there as placeholders, just because remember, if I would do 7a or 7b over 8b, the b's would cancel, and I would get that reduced proportion of 7/8. Okay, so that's what, the b is not necessary, but I don't know if there's a multiple. Okay, because I could have had, if b is 2, then that would have been 14 over 16, which reduces also to 7/8. So again, if you're having trouble with why I'm doing A and B's, please ask about that in class. All right, moving on. So XZ is 37.5 centimeters. XZ. So from here to here, it's 37.5 centimeters. Okay. So we need to find WY. So we're trying to find this one, WY. Okay, so all we're trying to do basically is figure out what are those A's and B's? What are the multiples here that create these proportions? And so they just gave us one piece of information, and that was XZ. And notice that we labeled XZ with this 5A. So that's going to help us figure out what that little A part is. So if I divide by 5, then I get A is equal to 7.5. Okay, so what does that mean? Well, that means that now I know that this isn't just 5, this is exactly 37.5, and this isn't just 2, that would be 2 times 7.5. So that would give me 15. So those top pieces, WX to XZ, is in this ratio. These are the actual numbers. 15 over 37.5. And remember, if I reduce that, I would get 2/5. Okay, so we just found A, that little bitty A, to figure out what are the exact measurements of that segment. So now we're going to do the same thing here with our WY. Now that we know the exact measurements, we can use that for our WY. All right, we know that this whole thing is 15. I'm running out of room. This whole thing, this is what I'm talking about. WZ, if we add the 15 plus the 37.5 together, I know the exact distance from W to Z is 52.5. So how am I going to use that to find my B's? Well, don't we know that this is 7B and this length is 8B, but together they equal that total distance. 7B plus 8B should equal that 52.5, that exact measurement. So if I combine those together, I get 15B equals 52.5. And now I'm just going to divide by that 15. And I'm going to get B is equal to 3.5. Is that what they wanted me to find? No. They wanted me to find WY. They want me to find what 7B is equal to. So make sure to plug that back in. So we're doing 7 times 3.5. So we're going to get 24.5. That would be our final answer. And that would be in centimeters. So I know this seems a little overwhelming just to look at this. This is visually obnoxious, but again, all we did was take those ratios and label them. And remember, a ratio is the reduced version of the actual. So that's why we used the A and the B. We used those to help us find what A and B were in order to find the actual measurements. Let's do one more, and then we'll do more in class. So we're going to find the length and the width of the rectangle, and they tell us that the perimeter is 420 yards. Okay, and they give us this ratio. The ratio of the length to the width is 17 to 13. So what do? We draw a rectangle. Okay, so if we call this the length and this the width, we know that 17, this is going to be 17 compared to 13, but again, we need like an A or a B Let's use A, that's fine. So I know this is 17A compared to 13A. And they tell us that the perimeter is 420. So I'm going to go ahead and label the other sides. This has to also be 17A, and this has to be 13A. So if I add all of those together, and set it equal to my perimeter, which is 420, then I'll be able to solve for A and get the actual length and width of the triangle. So let's do that. So we're going to get 60A is equal to 420, and then divide by the 60, and you should get 7. Oh. So remember, don't stop there. Plug that back in. So if we're doing 7 times 17, then this is going to be 119. And then 13 times 7 will give us 91. So our length is 119 yards, and our width is 91 yards.